our next speaker is Daniel Meyer from University of Liverpool, and he'll talk about weaving and folding maps. Please.
Okay. Well, thank you. Thanks for organizing this conference. Also, thank you for inviting me. I mean, you know, I kind of feel I really go to these conferences to see old friends, you know. So, but okay, so you know, then you also have to give a talk, you know. So, okay, this is just my excuse here to see some very good friends. Okay, so right. So what is weaving? Okay, so it's kind of like something that I have basically just very recently sort of invented, maybe. And what it is like, well, so you have two dynamical systems, and well, the dynamical systems are giving in symbolic dynamics by the shift, and you kind of put them together in a certain way. Okay, so here is my example how this is done. So you know, it's just the tent map. So here's just a tent map. So we have the unit interval, and so you know, unit interval is divided into the left and right half, and each one is mapped to the whole interval. Okay, so and here, right here, so this here is my Markov partition, right? So you know, like my two left and right intervals of my unit interval. Okay, all right, and so well, so you know, let's just code the left interval by 0 and the right interval by 1, right? And okay, so now, you know, restricted to each of these intervals, my tent map is just a homeomorphism, right? And so, you know, now I get, you know, basically symbolic dynamics. I have my interval and I kind of pull it back here a couple of times. And so, you know, I have a coding for a binary dyadic, of a dyadic interval of the nth level, right? So, you know, okay, so here's my unit interval. And so, you know, here just to illustrate, I have, you know, the dyadic intervals of level 2. And so maybe just the thing to note here is like the ordering of these intervals, not the standard ordering that you're used to, because that's just how these things work. And it's actually, well, the ordering is actually given by the parity lexicographic order, which is sort of, you know, you look at how many ones you have in your word, and then, you know, like, well, basically whether 0 is less than 1 or 1 is less than 0 depends on how many ones you encounter. If you encounter an even number of ones, right, then 0 is smaller than 1. If you encounter an odd number of ones, then 0 is bigger than 1, right? So that's a parity lexicographic order, right? And okay, so, and then of course we can code, you know, all points on the unit interval by binary words in this fashion, right? And then my dynamical system is given by the left shift. Okay. All right, and so I have made a choice here, right? So I've made, and the choice that I've made is that I said, like, well, my leftmost digits in my words are the most significant ones, right? So, you know, because when I write the words, I have to say, in which order do I write the words? Okay, and it's an arbitrary choice, right? So I could have, you know, just written my words in the other way around, right? So I start with the rightmost digits, and then I say, like, okay, my rightmost digits are the most significant digits when I write my words, okay? And well, what I'm doing now is that I'm taking my binary words and I'm looking at the incidence relation. What is the next with respect to both orderings, okay? So, and what I'm getting here is the following, right? So here I have my binary words of a length 4, right? And so, you know, so this is my leftmost word in my, you know, in my coding of dyadic intervals, right? And the next one, you know, when I add one, this is this one, and the next one is this one, and so on, okay? But this was sort of assuming that the leftmost digit is the most significant one, right? And if I sort of, you know, turn this around, right, and say the rightmost digit is the most significant one, then the next word happens to be this word, okay? And so if I have here the red, if I follow the red thing, so I have the dyadic words that are ordered of level 4, that are ordered with respect to the leftmost significant digits, right? And if I follow the blue one, okay, then I have, I mean, the same words, but the ordering is with respect to the rightmost digit being the most significant one, okay? And I get these sort of, how my dyadic words of length 4 in this case are sort of, how they sort of intersect with respect to my two ordinates, okay? Okay, now if we increase the length of words, this was length words of order 4, right? Well, then I get here this picture, and so the picture is sort of indicative that there is some sort of Cantor-Sept type thing going on. I don't want to get into this too much, okay, but I'm having these sort of, so here I have the red and the blue things, okay, and they're not really part of the space, but they sort of indicate how the words are sort of connected, right? If I go from here to here, I land over here, and so on, okay? So I get this sort of grid, right? And then at the boundaries of the grid, I have these sort of connections, right? And okay, so now we are good mathematicians. What are we doing? We take the limit, right? And what is it that when we take the limit? Well, in the limit, we actually get just a unit square, right? And again, the red and the blue things, they don't actually are part of the space, but they tell you how points on the boundary of the space are identified. So this point, so let's say t and 1 minus t here is identified, and so on, and each of these sides. And then you have this sort of self-similar picture, right? So here, this half here, these two things are identified. So you should really think of having a square, and then you kind of fold, and you kind of keep doing this. And well, and then if you do this, the quotient space is in fact the two-sphere. Okay, so I call this a Carvalho sphere because that's where it first appeared in this form, right? But okay, so we also had some dynamics, right? So the whole thing kind of started out with my tent map, right? And so the tent map was coded by the shift, right? And so, now this is sort of the limit of words that get longer, but now I want to have the words getting longer in both directions, because in a sense, I sort of forget about, I don't want to give preference to, let's say, when I only let the word go to infinity in one direction. So, the words get long in both directions. So I get bi-infinite binary words, okay? And so with respect to this symbolic coding, my tent map was the shift, okay? And so on this quotient space, right? So, my map is just the shift on this bi-infinite sequence, okay? And so the point here in this square is actually just represented by x and y. And so the x will give you, the positive indices, right? They will give you the x, right? And the negative indices, they will give you the y. And the coding here is a coding that comes from the tent map, okay? And so what is really this map, right? So the map is really, okay, here we have the square, and we think of the left as being coded by 0, the right as being coded by 1, and then we have basically an x direction, we stretch by a factor of 2, and in y direction, we contract by a factor of 1/2, right? And then we cut the rectangle in the middle and kind of stack it on top of each other. And if you kind of see here, the 1 is sort of upside down. So we kind of, make it upside down. And so the equivalence relation on the square are sort of the minimal equivalence relation that makes this into a homeomorphism. So for example, we have cut the thing in the middle, right? And kind of stacked it on top of each other. And so we identify the top and bottom. Maybe I should just use this one here, right? Okay, this is not bad. So we identify the top and bottom. And also, right, we kind of fold, so we fold this thing together, right? And so in order to make it a homomorphism, we also identify top and bottom, and then, we go, your identifications are sort of, we take pre-images and forward images, and we get all these identifications that you saw on the previous slide, okay? And so this map here is called the tight horseshoe map, right? And well, and so if we look at the x coordinate and we look at the restriction of the map to the x coordinate, it is just the tent map, right? So this thing is mapped to this, and this thing is mapped to this. So the restriction to the x coordinate is just a tent map. And if we look at the inverse map in this direction, then the restriction to the y coordinate is also the tent map. This thing is mapped to this, and this thing is turned around and mapped to this. Okay, so we have kind of, you know, two sort of tent maps, and one is in the x direction and one is in the y direction, but one is like in the, you know, in the future, and one is kind of in the past. Okay. And so I call this here the weaving of these maps, of the map, of the tent map with itself. Okay. And so this map is what I call a generalized pseudo-Anosov map. It has an expanding and a contracting direction with countably many singularities. So here's maybe just a picture. So a pseudo-Anosov map is a map that has an expanding, here x direction is expanding, and contracting direction, except at finitely many singularities. And when I have a generalized pseudo-Anosov map, then I'm allowing to have countably many of these singularities. Okay, and so the map that we had before, this tight horseshoe map on this Carvalho sphere, is such a map. So we don't have you know, finitely many singularities as we have for proper pseudo-Anosov, but countably many, and they sort of accumulate at, well, the origin in this case. Okay, so this is how the weaving works in this specific example. Okay, so well, let me give you the, I mean, the more general definition of the weaving. Okay, so we have a dynamical system, just continuous map, and it's expanding in a certain way on some metric space. Okay, and we assume it has a Markov partition. Okay, so, and if we have a Markov partition, we can code the map, let's say by the left shift, right? So here's our symbolic dynamics. So for example, in the example we had before, it was just like, you know, binary sequences, one-sided binary sequences, okay? And then we had the left shift, right? And then we have the projection from the shift space to our space, right? And this this diagram commutes, or put differently, like, you know, my dynamical system is a factor of the shift. Okay, but it could be, you know, some subshift doesn't need to be like a whole d-ary shift or something. Could be some subshift. Okay, and so well, so there is a general construction when you have a map that is not injective to make it a homeomorphism, right? And I didn't want to give like the whole general definition. It's not super hard, but there's something called the natural extension, which in a certain way is the smallest extension of the map to an invertible dynamical system. Okay, so there's, you look at all maps that extend this map so that it becomes invertible, and then the smallest one is in fact the natural extension. Okay, if we have given the map in this form as a factor of the shift, then there's actually a more easy way to describe what this natural extension is, right? So we have this one-sided shift, and we have all these sort of identifications, right? How do we make the one-sided shift into an invertible dynamical system? Well, we take the two-sided shift, right? So the natural extension of the one-sided shift is a two-sided shift, right? And so now we have these identifications, right? And we just shift all these identifications by the shift map around, okay? And so now we get all these identifications, and then we take the quotient by this identification, and that is actually one way of defining this natural extension. Okay, so basically, you know, we have all these identifications, and we shift it around by the two-sided shift, and now we get more identifications. And we have this diagram. Okay, so here, this is like two-sided shift. Okay, it's invertible, and here this is what is called the natural extension. And so, you know, instead of giving this sort of abstract definition, we can just, you know, define our natural extension in this way. We take, you know, the quotient by this two-sided shift by this extension of this projection map. Okay, so so the natural extension is, again, right, is a very natural thing to do in mathematics. It's the smallest way of making a non-invertible system into an invertible one. But the price that you pay, or depending on your, let's say, taste in mathematics, maybe you actually like such things, right? But the price that you pay is that the next natural extension typically becomes these objects that you get are typically complicated topological objects. Okay, so for the tent map, the natural extension looks like this. It's a cluster continuum. So you have a unit interval, and you take the unit interval product with a Cantor set. Okay, and now we have the red things, okay, which are actually not part of the dynamical system, but they tell you how the endpoints of these intervals, how they are identified. Okay, and that is what is called the cluster continuum. Okay. And so this is what is called an indecomposable continuum, meaning if you write this as a union of two continua, one of them has to be the whole thing. Okay, so if you have, let's say, the unit interval, where you can write the unit interval as a union of 0 to 1/2, 1/2 to 1. So you have decomposed the unit interval into smaller subintervals. But this one, you cannot decompose into smaller subintervals. Okay. And and so what is the natural extension map or the inverse limit map on this cluster continuum? It's like this. So you contract in this direction, you expand in this direction, and then you fold it back. Okay, so that is the natural extension map. And then if you restrict to, let's say, the x coordinate, that is again the tent map. Okay. Okay. Here's another very famous example of this type, which is a two-adic solenoid. So you take the angle doubling map, okay, and then the natural extension is what is called the two-adic solenoid, okay. And there's loads and loads and loads of things that has many, many interesting properties, actually a group, and it's also an indecomposable continuum. Okay, so so what now is the weaving of maps? Well, now we have two dynamical systems, F and G, defined on different spaces, okay? And well, we assume it has a Markov partition, so we have, we can represent these maps as factors of the shift, okay? And we can, take the natural extension of these maps, okay? So we have our two maps F and G, and we have the two natural extensions of the two maps, okay? So this is now on the two-sided shift, okay? And okay, so we can of course represent it by, let's say, the left shift, but okay, so whether we represent it by the left shift or the right shift, who cares, okay? But I want to represent this by the left shift, by the right shift, and this one by the left shift, okay? And the assumption that we're doing here is that these shift spaces up here are the same. So that's the assumption that I have to put in so that this is actually defined. So my shift spaces are the same. So if we have the full shift, that's not much of an assumption, but if we have a subshift, well, then it's an extra assumption. Okay, so and now I'm taking the union of these two identifications, and the way I think about it is like we have this two-sided shift, okay, and so these identifications that come from one map, they are identifications that sort of live to the left, and then I also have the identifications that come from a second map, and they kind of live on the right, okay. And now I'm using both identifications, okay. And then I'm doing something that is called the metric closure, which I have a slide that comes later on. I don't want to get into this at the moment, but I will talk about it a little later, because then it will be maybe a little more explicit when I talk about an explicit example. Okay. And so, well, what is now the weaving? Well, the weaving is, so I'm taking these identifications that come from the left and I'm taking both identifications at the same time, okay? And so the weaving of the two maps, right, is now just the shift, okay, descended to this quotient, okay? So, I mean, the way everything is done is that these identifications are invariant under shifts, okay? And therefore, the union is invariant under shift, so, everything is well defined, and so that is the weaving of these two maps, okay? Okay, so, and the way this really works is that you have these two strands, and typically, right, they are kind of in a sort of orthogonal way. You have one strand that goes like in one direction, and the other strand goes in the other direction, and you weave them together, and you get, like a bigger space, okay? So, okay, well, here are some examples of weavings, okay? So I weave tent with itself, okay? Then I get, in fact, like what I just showed you, right? The tight horseshoe map on the two-sphere, the Cavalier sphere, okay? And if I weave angle doubling with itself, I get what's called the Baker transformation on what is called the Chamanara surface, which has infinite genus and so on. But you can also weave together two different maps. Why not, right? So you have, okay. And I don't have a picture here. I have some pictures in my notes if somebody wants to see it. So it's kind of, it combines these identification for the tent map and the identification from the angle doubling map. So it's really kind of, you have infinitely many Möbius strips that are sort of glued together, on one side, and I don't know, that's what you get. Okay, so maybe have another example that I found kind of quite intriguing. So I take this algebraic number, so it's a solution of this quadratic equation. Okay, so it's, I mean, this is a minimal polynomial of this number, okay? And okay, so the map that I'm now considering is, multiplication by lambda mod 1. It's just, map on the interval to itself, okay? And so I get a Markov partition, right? So, 0 to 1 over lambda, multiplication by lambda maps it to the whole interval. 1 over lambda, 2 over lambda, again, maps this thing to the whole interval. And then I have this thing. This thing is, well, is not mapped surjectively to the whole interval, right? So, this point is mapped to 0, and this point here is mapped somewhere in here. Well, it's a point 0.062, and so on, okay? So it's mapped somewhere in here. This point is, in fact, a fixed point under this map. And, okay, so I have my Markov partition, okay? And from this Markov partition, I get a representation by the shift, but it's not the whole shift, okay? Because the map here is not surjective. So, if you have a 2 can never be followed by a 2, okay? A 2 will always be followed by something that's less than 2. And I don't want to give you, I mean, it's not super hard, but I don't want to give you the precise, I can tell you exactly what the subshift is, but let's not worry about this here. Okay, let's give it another name, okay? Okay, let's give it's some partition, okay? I mean, the only thing I really care about is that I can represent it as a factor of the shift. That's the only thing I care about, okay? To give a symbolic address to every point. It does. I mean, I can just, I mean, each point has just an address, right?
So if you had a fixed point there, would you get it marked?
Say again?
If you mark the fixed point.
I mean, there are many different ways of, yes, I mean, okay, so I can also, okay, here's a fixed point. I can also use the fixed point, I mean, okay, so, I just, okay, so, this interval is divided into 3 intervals. This interval is divided into 3 intervals, right? And so, okay, I know exactly where this point here is mapped to because it's a fixed point. So the symbolic address of the fixed point is 2, 1, 1, 1, 1, 1. Okay. And that's really the only thing I need. So, I mean, again, I only care about that it's a factor of the shift, nothing else. Okay. I mean, again, right? I just map them and, I see how they're subdivided, and that's it. I don't need anything else. It's not a shift of finite type. It's not a finite type. It's not a finite type. Okay, and so why I'm interested in this? Well, if I weave this here with itself, what I actually get is this map on the 2 torus, right? Which is the plane modeled out by z squared, okay? Which is known as Arnold's cat map, okay? So, and in a sense, like when you talk about pseudo Anosov, well, the first thing that you want to ask is maybe, well, what about Anosov? Okay, that's sort of the easiest Anosov map. Okay, so has an expanding direction, has a contracting direction. So the reason I picked this number is really that it's the expansion factor of the cat map. Okay. And if I take a different polynomial, this thing here, okay, and I take, the bigger of the 2 solutions of this quadratic polynomial, I get another Anosov diffeomorphism on the 2 torus, which is this, descended to the 2 torus. Okay, so yeah, so weaving this with itself gives you like an Anosov map on the 2 torus. Okay. So let's see, how much time do I have? When did we start? 45? Or, okay. Okay. And now for something completely different, or maybe not. Let's see. Okay. Which is the second thing in my talk, which is a folding map. And here's a simple example. Okay, so I take just a square, and I divide the square into 4 squares of half the size, right? And so I map this square to this square and this square, well, also to this square, but by an orientation reversing thing. So the way I really, like to think about it, so here's my square, right? And I fold it and I do it like this, okay? And then I stretch it by a factor of 2, but my paper does not allow me to. So this is where you have to use your imagination, okay? And so that's what I call a folding map, right? And so, okay, so these things I call one tiles, and they're colored black and white depending on whether they're orientation preserving or orientation reversing mapped, okay? And okay, so you can write down a formula for this map. Here's a formula. It's just in X and Y coordinate, you just have the 10 map, okay? So, okay. All right, and so, well, so here's the more general definition. Okay, so I take, here I had a, a square, right? But I could have a triangle or, hexagon or something. Okay, so just a k-gon, okay? I don't know, maybe here I have a triangle, right? Has 3 vertices, right? And okay, and it's subdivided into other k-gons in a topological fashion. It doesn't need to be like, in a sort of self-similar fashion or what, but it's just subdivided into some other k-gons, okay? And then on each of these smaller things, maybe I should go back to my square. So on each of these smaller things, right, I have a map that maps this to the whole thing, okay? And I also, but I want this map to be cellular, meaning that, you know, vertices go to vertices, edges go to edges, okay? And also I want that the vertices are sort of mapped to itself as a set. I mean, not each vertex is mapped to itself. Where's, okay. Or maybe I can actually look at it in the reverse order. Instead of mapping the small thing to the big thing, I can think of mapping the big thing to the small thing, and then it's just an iterated function system, okay? And now if I kind of pull things back, right? So, you know, each square is sort of subdivided into 4 squares and so on. So I get, you know, tiles of, you know, of level n, okay? And I want the map to be expanding, meaning that the tiles, the size shrink to 0, okay? And the way I think about it is this is like a 2-dimensional analog of a tent map thing, okay? So each one is mapped to the whole thing, and you kind of fold, you know, have an annotation preserving, orientation reversing, and so on, okay? Okay, here are just some examples. I mean, just because they're easier to draw, I kind of, you know, had some examples here where, you know, it's really subdivided into things that are self-similar. But it doesn't need to. So, you know, here this is just kind of topological. It looks, this is not a triangle, but, you know, it's a triangle because I, you know, put 3 vertices here on each thing. So therefore it's a triangle, and I can just map it over in some fashion. I don't care in which fashion it is actually mapped. Okay, and so, well, why do I actually care about folding maps? Well, I mean, one thing is that they're sort of 2-dimensional generalizations of tent-type maps, right? But I really care about this because I think of them as quotients of certain rational maps. Okay, so here's an example, right? So here's 1 minus 2 over z squared. It's just a rational map, okay? And it's a real rational map, so the coefficients are real numbers, okay? And so what does that mean? Well, it's invariant and symmetric with respect to the real line. So the real line is mapped to itself. And if I kind of conjugate, you know, so it kind of commutes with this conjugation. And well, it's also very nice. It's a post-critically finite map. So it has 2 critical points, 0 at infinity. And this is how they're mapped. In particular, the forward orbit of all the critical points is finite, okay? It's post-critically finite. And well, and they're all contained, in fact, on this real line, which is where the map has a certain symmetry, okay? So, and it's also expanding. I mean, okay, so it's actually a lattice map. The Julia set is the whole sphere. So what does that mean? If I pull back the real line and look at how the sphere is sort of subdivided, the tiles shrink to 0, okay? Well, so if you encounter something in mathematics and it has a certain symmetry, well, one thing that you should at least try out is like, well, mod out by the symmetry and see what happens. And that's what we're doing here, right? So we just identify z and z bar, right? Because our map has a certain symmetry, right? And now, you know, let's say a fundamental domain of the dynamics with respect to, you know, the symmetry is just, let's say, the closed upper half plane. So, you know, it's just a closed disk, okay? And in fact, for this specific example that I showed you, 1 minus z squared over 2, when I do this, it is actually exactly this type of map, okay? And it doesn't need to be actually a holomorphic dynamical system, so you can also think of expanding first map, so it's a branched cover of the 2-sphere. It's not necessarily holomorphic, and if it has a certain symmetry, you know, there is some sort of Jordan curve, and you know, like the map commutes with respect to reflection along this Jordan curve, you can do exactly the same thing. And well, conversely, if you have such a folding map, you can kind of glue, oh, they kind of have different sizes, but you can glue 2 copies together and you get a sphere, and then, you know, on the sphere you have this dynamic system. So basically, from a folding map, you can get an expanding Thurston map. So basically, you know, like a folding map in my mind is really nothing else than an expanding Thurston map with a certain symmetry. Okay, so from symmetry, you can model by the symmetry, you get a folding map. From a folding map, you glue 2 things together, you get such a rational map, or maybe it's not rational, but just expanding first map. So that's why I'm interested in. Okay. And maybe kind of the more, let's say, conceptual way why I'm interested in this is Sullivan's dictionary. So, okay, what is Sullivan's dictionary? So we have, let's say, our two big fields of, let's say, conformal dynamical system. We have Kleinian groups, discrete groups of Möbius transformations. Typically, these are groups of hyperbolic 3 manifolds, and then we have complex dynamics. We iterate some holomorphic dynamical system, and okay, so both are sort of holomorphic. So in a sense, it's not really too surprising that you kind of encounter similar phenomena in these two fields. But here I want to actually focus on what are the differences, okay? Well, in complex dynamics, you usually deal with dynamical systems that are non-invertible. Whereas in Kleinian groups, you deal with Möbius transformations, which by definition are invertible. And okay, so for Sullivan's dictionary, Möbius transformations you can view in two ways. Okay, so you can either think of a Möbius transformation as being an automorphism of the unit sphere or an isometry of hyperbolic 3 space. Okay, so and the sort of back and forth between, let's say, the hyperbolic 3-dimensional picture and, let's say, the conformal, let's say, 2-dimensional picture. That's sort of one thing that's, you know, incredibly powerful when you talk about Kleinian groups. Okay, and well, when we have when we talk about complex dynamics, you know, we don't really have, you know, like an action of on hyperbolic 3 space. Okay, and okay, so when you talk about Kleinian groups, pseudo-Anosov maps play a very, very important role. Okay, so for example, when you talk about manifold that's fiber over the circle, the virtual fibering conjecture, and so on, and you know, in complex dynamics, we don't really have a corresponding thing that you know has a sort of contracting and expanding behavior. So we don't really have that. Okay, and of course when I say like, okay, we don't, I mean there are some results that go in this direction, and I don't really want to talk about it too much, but let's say, you know, they're still not quite what we expect in the Kleinian group case. Okay, so what I want to be doing is to extend my square folding map to something that becomes invertible. Okay, so here's my folding map, right? So here's what I'm doing with the folding map, and I told you the map is not invertible, but in a sense, like, okay, you know, like here I kind of unfold it, and so I have inverted the map. Why is that possible? Because I'm sort of a little lying, right? So my piece of paper actually has a certain thickness, right, which actually does not allow me to really, you know, map it completely to the square. But I kind of, you know, I'm kind of stopping here because the thickness really, you know, does not allow me to map it to the square. Okay, and so, well, instead of having a thickness that's very, let's say, thin, let's just say like the thickness is 1. Okay, so I take just the product of the square with a unit interval, and I get the cube, which you have here, right? Okay, and so now, right, I am expanding in the z direction by a factor of 2, contracting in the t direction by a factor of 4, right? And then I chop these things up and kind of stack them on top of each other, right? And the stacking is exactly kind of, you know, what I have here, right? So I have here my 4 little squares, right? And so now instead of having my thickness to be some epsilon, right? My thickness is now, because it was 1 and I had kind of contracted it by 4, now my thickness is 1/4, so I get the cube again, right? And so this is my map, right? And okay, so on each of these sort of what I call wedges, or like, you know, pieces of cake, if you want, right? You know, the map is well defined, okay? And if I look now what happens to the map restricted to the z coordinate, well, you see that this is exactly the folding map, okay? But what I can also do is I can look at the inverse of the map, okay? And I look at what happens to the t coordinate, right? And so this thing is mapped to this. This thing is mapped to this, but it's turned upside down, okay? So restricted to the t coordinate in this direction, the map is the second iterate of the tent map, okay? So in the z direction, this direction, it's my folding map. In the t direction, this direction is my second iterate of my tent map, okay? And okay, so now, right, in order to kind of stack this on top of each other, right, I had to kind of cut these things, right? And so now, well, the map is not really, well, it's not even a map, right? Because the points that are sort of where these two pieces of cake intersect, well, got mapped either to here or here, right? So what I want to be doing is, well, I want to, identify these things so that things are sort of well-defined again, right? So, and well, maybe I should just say, right, my cube, right? Well, it's just a cube, right? So it gets the Euclidean metric, and it also gets like three-dimensional Lebesgue measure. And so, the map is measure preserving, and in a sense, it's a pseudo-Anosov map, okay? And I want the global homeomorphism that restricts to my, maps that when I start out with are only defined on these pieces of cake, okay? But what I get again, right? So, when I have like points that are in the intersection, they get mapped to two different points, right? And also, right, I mean, I may have two different points that are mapped to the same points, right? And so these are points really where I kind of fold things together. So, this point and this point, they get mapped to the same point on top of each other. So I also want to identify these points, okay? And so I identify these points, okay? So, put differently, I want to have an equivalence relation that is exactly defined. I have these points. If they are identified, then in the pre-image, in the image, and in the pre-image, they should also be identified, okay? Okay, and here's what I sort of pushed a little aside before. So I also want to take the metric closure. So what is the metric closure? Well, so I have an equivalence relation, right? And if I am inside of some equivalence class, right, I can travel for free inside of the equivalence class, right? And if I go to a second equivalence class, I just write down what the distance is from this point to this. But then I'm allowed to travel for free in this equivalence class, and then I get to another equivalence class, and then I have to kind of pay the price for what the distance is of this equivalence class. But within an equivalence class, I travel for free, okay? And so, but then if I have 2 points and the infimum of some such chains of the, this length that I have defined, if this is 0, then they also should be identified, okay? So this is what is called the metric closure. Okay, so here is, okay, so here is the main theorem, which is that, these maps actually descend to this quotient. And okay, and so, well, then this map on this quotient is in fact homeomorphism, and this quotient is in fact then a 3-sphere. Okay, so you have this sort of quite complicated identifications, right? And it looks, you have to actually spend, well, depending on, we spend actually quite some time. But it is, at the end of the day, it's just a 3-sphere, okay? And, well, and this map is, in fact, a generalized Anosov map, so it has this expanding direction and this contracting direction, okay? And what this map really is in terms of what I defined earlier, okay, it's really the weaving of this, this folding map and the tent map. And I tried to draw a picture on my slide and I failed miserably. But, so you have these sort of, well, now I failed miserably on the board, but you have these sort of squares, right? And so, they're identified, right? And then, from the weaving, you get this sort of, strand that sort of weaves sort of orthogonally kind of around this and sort of weaves these all together, okay? And that is actually what this map is, okay? And really, in a sense, like, the theorem is really the second part, okay? So to really show that this is a 3-sphere, that's really where we have to work, okay? The other things are sort of not that hard once you have set up, everything correctly, okay? And well, and the theorem I only formulated here for my square folding map, but it is actually true for all these sort of folding maps. But is somebody asking a question, or is that? We have to have some conditions on the way the tiles are what we call stacked. So really, when we talk about stacking, right? What we really mean is in which order the one tiles are kind of put on top of each other. Okay, so one thing is maybe not so difficult is like the way these things are identified on each side, they should not be crossing, right? So you cannot identify 1, 2, 3, and 2 to 4. They should not be crossing. So that's maybe not too surprising. And the other thing is that the tiles have a color, right? And the black and white colors should alternate, okay? Because that would kind of mean that the other map that you weave is sort of like what we call a sawtooth map, and otherwise, well, then these things don't really fit together in the way that we want them to. And then there is sort of like a last condition, which is maybe not so obvious, but so when you kind of fold these things, you have these sort of raw edges, okay? And okay, maybe I'll use. Yeah. Okay, so here I have some raw edges, okay? And what I'm not allowing is that the raw edge is sort of trapped between two things that are identified. Okay, so these are things, so these are the conditions that I need to sort of put on these things. And also, this is also one of my folding maps, but as you can see, right, so there's one tile that's black and 3 tiles that are white. So, no matter how I stack them, right, I want black and white to be alternate, but I have 1 black and 3 white, so I cannot put them in an alternating fashion. So this is actually an example where this does not work, okay? But that's from the things that I showed you, it's the only example where this doesn't work, but in all the other cases, it does work, and you do this operation, and you get actually this sort of generalized pseudo-Anosov on a proper 3-sphere. And okay, so there are many more examples. So this sort of mod 1 map, you can sort of you can change it a little, and then you actually get also like generalized pseudo-Anosov on some surface of infinite genus, and then like other example where I had like some surface of genus 8, like a pseudo-Anosov map. One thing that I kind of pushed very much here in the background, these identifications of these sequences can in fact be done using the iterated monodromy group, right? And so the iterated monodromy group usually acts on sequences like binary or dyadic sequences, okay? But now we have sort of 2 groups that act on bi-infinite sequences, so and one sort of acts from the left and one sort of acts from the right. So there's, I think, still a lot to be done. So for example, at some point I actually thought that this example with the cat map, that there is some sort of Grigorchuk group sort of inside. I get super excited, and then I because I kind of showed this is sub-exponential growth, but then I actually showed that it's polynomial growth, so I didn't quite get what I was hoping for. But I do think that there's still a lot of interesting things still to be done. And okay, so here I only kind of wove, let's say, these sort of folding maps just because I was able to get like a nice space in the end, like a 3-sphere. But of course you can also just instead of having the folding map, you can have like a whole rational map, right, without taking this quotient, right? And I mean, this works. What we get doesn't seem to be a particularly nice space, okay? So then it's sort of the question, what is it good for, right? And you can weave all the sort of things with itself, and then you can actually also ask what happens in higher dimensions. And in order to prove that it's a 3-sphere, well, we're using some quite old geometric topology result, and some of them are really only formulated for 3 dimensions, and I'm not 100% sure whether they can be generalized to higher dimensions, or so we don't know really. And then of course you can ask like, okay, you have a map. You know, let's say it's a pseudo Anosov or generalized pseudo Anosov or something like that. You know, then you can ask like, well, does this arrive? You know, arise as a weaving? You know, does this come from the construction? We don't know. So yeah, so this is how far we got so far, and I think there's still many interesting things to be done, but this is all I wanted to say. Thank you.